We're excited to have you here today. This is the second installment of our virtual meeting. So this was originally a meeting that was scheduled to happen in October in Seattle. And then we've since then, because of the shutdown, split it into two Zoom meetings, and then we'll have an in-person meeting in May. So the general structure and format, if you weren't here last time, is the goals are to outline and showcase some of the existing research in the field that it relates to ground motion modeling, to define some priorities as a group or community moving forward for ground motions in Cascadia, and then think about how do we want to build out collaborative projects in community. So on the 10th of January, we had a number of presentations and breakouts that were focused on outputs. So effectively, what do we need ground motion estimation to address in Cascadia? And then today we're going to be talking about inputs and data. So what exists that we can use, and then methodologies and putting it all together. And then in May, we'll have the in-person workshop. So I think stay tuned, and there will be some more emails coming out about that soon. So for today, we're going to have a handful of presentations about inputs. We'll have a short break and some Q&A, and then we'll move into the methodology section and have a discussion breakout at the end. So we'll start off in the beginning. We'll have Zoe Krauss who'll be talking about what we have for existing earthquake catalogs and seismicity. Audrey Dunham's going to look at how dynamic rupture simulations can potentially be used in supporting ground motion models. Pieter share will talk about some updates to the CRESCENT Cascadia velocity model. And then Alex Grant will talk about geologic constraints on Cascadia paleo-earthquake shaking. And then after the break, we'll have Greg Lavrentiadas talking about non-ergodic ground motion models, and then at least Gabriel talking about near-instantaneous physics-based modeling. So I think we'll probably get started if you're all ready for that. Should we start with Zoe?
Hey, all right. Hi, everybody. My name is Zoe. I am a postdoc at the University of Washington at the Pacific Northwest Seismic Network. But today I'm going to be playing the part of Renata Hartog. So everybody, please be patient with me. Renata was asked to give this talk on kind of the background seismicity catalogs and what's available in Cascadia. So, but wasn't able to make the new meeting time. So asked me to present her slides. So if I say anything that doesn't make sense, please forgive me. And also, most questions should be directed to Renata. Her email is here. I'll show this at the end as well. But also, if you have any questions, I can do my best to connect you with her. But anyways, yes, like I said, we were asked to give a presentation about earthquake catalogs. So here goes. This is a lot of text, but essentially the question is kind of what is available online publicly since the NGA subduction zone database was developed about 5 years ago now. What's the current state of the art, state of the union, and where can we find things that are valuable to future ground motion validation or databases in general? And so I'll kind of step through where everything is and what everything is. But in general, there is a lot more data, and hopefully you'll step away with that takeaway. So starting with the earthquake catalogs for the Pacific Northwest, the first thing that we're going to focus on is just the official catalogs. So these include historical events, and they are generally complete for events large enough to produce felt shaking, easily complete to about magnitude 2.5 or so. They're also more homogeneous across networks, across kind of data quality, and they also just have the best APIs. They're the easiest to use, easiest to access. And in general, we have lots of small earthquakes in the Pacific Northwest, but this talk is just trying to focus on the larger earthquakes that are more relevant to ground motion modeling. There's also the strong motion catalogs, which I'll talk about a little bit. These are the earthquake parameters that are more processed for engineers. You'll find overall that the data for seismologists is more easily accessible, but process data for engineers is a bit more difficult to access. And then also, just to be aware, there are also research catalogs. So for example, Ian Stone's and Emily Morton's offshore catalogs that use the Cascadia Initiative data. Not going to focus on these catalogs in this talk. In general, they kind of include smaller magnitude events. They focus on adding in data from temporary experiments, might use more high precision relocations, but something to be aware of as well if you're looking in a specific area. But we're going to focus on these official catalogs. So the number one source, which I'm sure many of you are familiar with, is the ANSS ComCat. This is the official catalog for the US, also including global events. And this is the main landing page for that and has lots of kind of different data products you can parse through. And so the ANSS pulls data from several authoritative contributors. So these are the regional seismic networks. Washington and Oregon, the Pacific Northwest, and Columbia, it's the National Earthquake Information. And for events occurring kind of within the Canadian network, Natural Resources Canada is probably the best source for the most accurate source parameters there. But in general, in the PNW, did I pause? I'm worried about my internet connection.
You did momentarily, but it seems like it's all right now.
Okay, continue. Okay, sorry about that.
Yes. That's right.
Okay, so in the PNW, most of the 3.5 plus events have an ANSS shake map with associated station data that's coming from the PNSN. For larger earthquakes, there's also finite fault models. These are what's ported and used in the event parameters for NGA projects. And so all of these things can be accessed through the website or can also be collected kind of programmatically, queried through code, etc. And then, yes, this is the landing page for Natural Resources Canada. That's the link here. I believe these slides will be online, so hopefully these resources are useful. But what is actually in the Comcat catalog? So just to kind of give you an overview, this is the 4.5 plus since 1990. And as you can see here in the PMW, we have a very little seismicity on land. Most of it is offshore within the Gorda Explorer plates, within the fracture zones, et cetera, basin and range province. But specifically, if we look instead what is in the database since 2015, which is the year the NGA subduction database starts, we see even fewer. There's only been 6 M4.5 events kind of near the Pacific Northwest areas, 37 offshore and 37 in Mendocino. But what Renata wanted to kind of point out is that it's valuable to get familiar with the search tools in this type of catalog. For instance, if you lower the minimum magnitude to M4, you'll find 4 more events in the Seattle region, a recent 4.4 outside of Salem. So kind of if you are able to play with this, this can be a really valuable resource. Okay, so that's the kind of official catalog, but what about actual kind of morpho engineering, the event associated strong motion parameters? So there's kind of 4 main things that Renata wanted to point out. First, that the data used in the ANSS shake maps is available in Comcat or from the regional seismic networks, such as the PNSN. There's also data archived at the Center for Engineering Strong Motion Data, the NGA databases themselves, and then of course, you can always measure these yourself from full waveforms. So I'll kind of step through each of these in a bit more detail. So the Center for Earthquake Strong Motion Data, strongmotioncenter.org, this automatically grabs data from the PNSN stations, from the UO networks and the UW networks for earthquakes with magnitude 5 or greater. But they also process data if an event is broadly felt. And so that's kind of a manually triggered process, but kind of all relevant ground shaking earthquakes should be included in this database. And you can kind of look through the archive here. And then there's also the NGA subduction database. So this includes relatively fewer earthquakes. It's a more strict criteria to be included, and some of them are quite small, down to M3.3. And you can kind of see the data coverage over here on the right. And so the orange line here is what delineates the volcanic arc. They don't include any events further east of this. So for example, a 4.5 near Rainier or something near Hood. But there's also no events west of the Cascadia deformation front. So that kind of limits it to this specific area. But there's a lot more kind of information provided for these earthquakes. There's peak ground acceleration, velocity, and displacement. And there's also the 5% damped peak spectral acceleration. That's that essay listed here at a wide range of periods from 0.01 to 20 seconds. And so, for example, if you dig into the NGA subduction data process, this is kind of the types of data that's available. So there's many event parameters included to facilitate regressions of the ground motion parameters with respect to different event characteristics. So this can be a really rich resource. Okay, so those are kind of the ground strong motion parameters, but also you can always pull data yourself. So Renata kind of wanted to point out how much the data density and quality has improved over time. So to really drive that home, I'm going to flip through many years here. So starting in 1990, we have the broadband sensors on the left, strong motion on the right. You can see pretty sparse to begin with. 95, we maybe start to fill out a bit more azimuthal coverage. 2000, similar story. 2005, you can start to see some more kind of temporary deployments. 2010, that's when things really start to get filled in. 2015 here, you see the temporary Cascadia initiative array, more temporary arrays and more strong motion sensors as well. 2020 is when things really start to fill out. This is when kind of the earthquake early warning build out began. And then here in 2026, we see a huge increase. So this is kind of due to the shake alert build out. Lots more 3-component data now. But in summary, as kind of takeaways, if validate synthetic seismographs, a drive would be to 2000. That's when you're going to get better azimuthal coverage. But keep in mind, oh, am I back? Sorry about that. All good. Okay. The only large inland event, which is the Squally, was in 2001. So that's kind of before we had a lot of these really dense stations. But also another thing to keep in mind, for the best spatial coverage, it would be best to focus on M4 plus post 2020. And like I mentioned, that's when we have those 3-component digital stations thanks to Shake Alert. And so for accessing that waveform data, that can be retrieved via the FDSN standardized web services, also archived at EarthScope. Northern California data can be retrieved directly from the NCEDC, and Canadian data can also be retrieved from NRCan. So that is all I have for slides. Again, questions should go to Renata, but I'm happy to take them for you. But anyways, yeah, hopefully that's helpful. Thanks so much.
Thank you, Zoe. That was really great. I know you said send them to Renata if anybody has any quick questions that I don't know, Zoe, if you feel you're comfortable answering or that we could relay to Renata.
Yeah, we can see.
Yeah,
either way.
Either raise your hand or put them in the chat.
I can write them down maybe.
Okay.
But yeah, hopefully these slides themselves are helpful too when they're on the website.
Yeah, these are really helpful. It's cool to see the station build out.
Yeah.
Over time.
It's been a busy past 5 years, in my understanding.
Yeah, it looks, I don't know if we have any additional questions. Maybe we can move to the next speaker. And if
Hey, all right. Hi, everybody. My name is Zoe. I am a postdoc at the University of Washington at the Pacific Northwest Seismic Network. But today I'm going to be playing the part of Renata Hartog. So everybody, please be patient with me. Renata was asked to give this talk on kind of the background seismicity catalogs and what's available in Cascadia. So, but wasn't able to make the new meeting time. So asked me to present her slides. So if I say anything that doesn't make sense, please forgive me. And also, most questions should be directed to Renata. Her email is here. I'll show this at the end as well. But also, if you have any questions, I can do my best to connect you with her. But anyways, yes, like I said, we were asked to give a presentation about earthquake catalog. So here goes. This is a lot of text, but essentially, the question is kind of what is available online publicly since the NGA subduction zone database was developed about 5 years ago now. What's the current state of the art, state of the union, and where can we find things that are valuable to future ground motion validation or databases in general? And so I'll kind of step through where everything is and what everything is, but in general, there is a lot more data, and hopefully you'll step away with that takeaway. So starting with the earthquake catalogs for the Pacific Northwest, the first thing that we're going to focus on is just the official catalogs. So these include historical events, and they are generally complete for events large enough to produce felt shaking, easily complete to about magnitude 2.5 or so. They're also more homogeneous across networks, across kind of data quality, and they also just have the best APIs. They're the easiest to use, easiest to access. And in general, we have lots of small earthquakes in the Pacific Northwest, but this talk is just trying to focus on the larger earthquakes that are more relevant to ground motion modeling. There's also the strong motion catalogs, which I'll talk about a little bit. These are the earthquake parameters that are more processed for engineers. You'll find overall that the data for seismologists is more easily accessible, but process data for engineers is a bit more difficult to access. And then also, just to be aware, there are also research catalogs. So for example, Ian Stone's and Emily Morton's offshore catalogs that use the Cascadia initiative data. Not going to focus on these catalogs in this talk. In general, they kind of include smaller magnitude events. They focus on adding in data from temporary experiments, might use more high precision relocations, but something to be aware of as well if you're looking in a specific area. But we're going to focus on these official catalogs. So the number one source, which I'm sure many of you are familiar with, is the ANSS ComCat. This is the official catalog for the US, also including global events. And this is the main landing page for that and has lots of kind of different data products you can parse through. And so the ANSS pulls data from several authoritative contributors. So these are the regional seismic networks. Washington and Oregon, the Pacific Northwest, and Columbia, it's the National Earthquake Information. And for events occurring kind of within the Canadian network, Natural Resources Canada is probably the best source for the most accurate source parameters there. But in general, in the PNW, did I pause? I'm worried about my internet connection.
You did momentarily, but it seems like it's all right now.
Okay, continue. Okay, sorry about that.
Yes. That's right.
Okay, so in the PNW, most of the 3.5 plus events have an ANSS shake map with associated station data that's coming from the PNSN. For larger earthquakes, there's also finite fault models. These are what's ported and used in the event parameters for NGA projects. And so all of these things can be accessed through the website or can also be collected kind of programmatically, queried through code, etc. And then yes, this is the landing page for Natural Resources Canada. That's the link here. I believe these slides will be online, so hopefully these resources are useful. But what is actually in the ComCat catalog? So just to kind of give you an overview, this is the 4.5 plus since 1990. And as you can see here in the PNW, we have a very little seismicity on land. Most of it is offshore within the Gorda Explorer plates, within the fracture zones, et cetera, basin and range province. But specifically, if we look instead what is in the database since 2015, which is the year the NGA subduction database starts, we see even fewer. There's only been 6 M4.5 events kind of near the Pacific Northwest areas, 37 offshore and 37 in Mendocino. But what Renata wanted to kind of point out is that it's valuable to get familiar with the search tools in this type of catalog. For instance, if you lower the minimum magnitude to M4, you'll find 4 more events in the Seattle region, a recent 4.4 outside of Salem. So kind of if you are able to play with this, this can be a really valuable resource. Okay, so that's the kind of official catalog, but what about actual kind of more for engineering, the event associated strong motion?
For organizing this and for the GMM group for steering it all. As mentioned, so I'm Pieter Scher, and I'm going to give a little bit of update on what's happening within the CVM working group and how we are steering this effort towards Crustal scale features and shallow features as well. And in the previous 2 talks were actually great segues to this topic. But just to give you a note, and so I'm giving a general overview of the year, but our postdoc here at OSU, Dr. Zhengwan Zhu, who's also on the call, he's really stuck into the nitty-gritty of all of this right now. And so if there are any technical questions that come up through this talk, I'm definitely going to punt it towards him. And so those of you familiar with the CVM efforts and our workflow, this is not new, but to some of you it will be new. And so essentially how we're going about building this massive scale model, seismic property model for Cascadia is in this like multi-scale nested type fashion. And so we start at the very like large scale and we're looking at coarser features. And then, and that's what we call the generation 0 to 1 models. If you were on the town hall yesterday, you would have heard Dr. Ben He talk about how they've produced this model. And so within this structure, we embed high resolution, shallower crustal scale features. And that's what we are referring to, right? Or that's what I'm referring to right now as these Gen 2 models, which is B in the figure. And that's going to be the focus of this talk today. And so why do that? Well, firstly, it ties in with a lot of other efforts within CRESCENT and elsewhere. For example, the community fault model group, they are resolving crustal faults. And so some of these crustal structures are going to correlate very nicely with that. So there's a bit of a science collaboration there. Number two, and maybe most importantly, we can't just go ahead when it comes to ground motion modeling and simulations and take these high resolution geotechnical layers or topography data and smack that on top of our Gen 0 to 1 coarser scale model of Cascadia. It's not going to be the true Earth. And secondly, it's going to produce all types of inaccuracies in ground motion simulations. And that'll show up once we compare that to real recordings. We do it because, the NSF supports us to do exactly that. And on that point, this always comes up during these type talks. But essentially, what we're focusing on here are the classic elastic properties within this space. So your P wave velocities, S wave velocities, densities. We are not focusing as of yet on any attenuation or anelastic or damping or Q properties within this model space for the simple reason that that's not what we proposed. However, we fully agree with the community that these parameters are extremely important to resolve. Eventually, that's going to require additional support. That's also a focus on some of our SIG grant priorities. So that's one way how we're trying to push the type of work happening in that direction. But just so you know, we're not initially focusing on that in addition to the classic elastic properties just yet. So talking about scales that are tractable when we think about high resolutions. And so the first iterations of the CVM model space, it covered the entire Cascadia footprint and beyond, in fact. And that's what's indicated by A on the left here. And we can do that because we're focusing a pretty long wavelength and lower frequency data. And so that's a tractable problem. But in the case, once we want to focus in and go into higher resolutions, which is highlighted by B in this figure, it becomes difficult for two reasons. We don't have equal data density in all parts of Cascadia. By data, I mean it could be a seismic station network. It could be seismic events, whether these are man-made or natural. But even if we had equal density everywhere, it becomes a computational problem on the other side of that. And so essentially what I'm showing you on the right here, if you try and focus on the region, let's say 150 kilometers by 150 kilometers, if you start looking at high and high frequency data, you're going to need more and more CPU cores, and those increase exponentially the higher the frequency you go. And if you want to focus on a higher or a larger crustal area, you will need more and more computational cores to resolve those same high frequencies. And it's going to probably cost you a little bit more time. And so we have to focus on an area. And so our first little area within the crust that we are working on right now is the Willamette Valley and Basin. The reason for doing that is that, maybe compared to the Puget Sound area and the Seattle Basin area, which Aubrey just talked about in the talk before, the Willamette Valley is a little bit more poorly known. And so we decided to shift our focus to this area at first. Some of the key parameters of that space is shown on the page over here, just to let you know that what we are incorporating in this problem is anything we can find. So broadband data, strong ground motion sensors, nodal arrays, and all three components in the cases where these are available. As Zoe elaborated in the first presentation, we've really seen an increase in the amount of all these sensors in the Willamette Valley and elsewhere, dramatically over the last few years. And so there's a ton of new data that we can employ within this problem. For those interested, we've downsampled these data sets to 20 samples per second. That's more than enough to cover our bases in terms of ambient noise. But eventually, we do want to look at the few local earthquakes we have within the crust in the area to improve this model space even more, and any other seismic sources that might be of use to build this model space, like quarry blasts, for example, which happen often on a daily basis within the Willamette Basin Valley and elsewhere. And just given our station density on the left over here, at its densest point, which is around the Portland area, our mesh size will probably be on the order of 0.5 kilometer to 1 kilometer, just to give you a sense of the spatial scale that'll come out of this type of modeling. And what we did even before fiddling with the data is that we wanted to modify some of these adjoint tomography and full waveform codes to make sure it'll work with these multi-scale, multi-type data. And so, long story short, it does. We've got it to work, and as a first step, we really pushed it to its limits. We focused on a nodal deployment that happened in 2022 in Corvallis and the surrounding area here in Oregon. And we tried to fit and model data up to 2 hertz in some cases. And so what's shown to you on the left here is an S-wave sensitivity kernel from that process. And this is after one iteration. And so what it essentially is showing you is that in these blue regions or negative amplitudes for the sensitivity kernel, we need to update the reference or starting model by increasing shear velocities in those areas. And the red blobs mean the opposite. The reference or starting model is a little bit too fast compared to the data that we're employing. And some of the details on the right over there, we're looking at ambient noise here alone. We've got multiple virtual sources. Anyway, so the tool works at this scale. The scale of the Willamette Basin and Valley is much larger. And so we know that's going to work in this extreme case. So we're pretty confident once we apply it to the data at larger scale, it'll work just as well. And so now that I've got your collective mouths watering, the model is not ready. It's obviously quite a process. And so definitely by the time the next meeting comes around, the GMMM topical workshop in May, we'll have this model for the Willamette Basin and Valley ready, and we can then dive into the details of that. Related to that model, one of the big things that we're thinking about and that we're going to have to get creative with is dealing with data and model uncertainty. I know this is very important for the ground motion modeling group, and so it's difficult computationally in this case because everything I described to you up to this point is producing a model with various iterations using several thousand cores. That'll just produce one model. To get to uncertainty, you probably have to apply some sort of bootstrap approach where you figure out in different parts of this model space, given the quality of data, how well is the model resolved. That's going to include a lot more simulations and adjoint tomography runs, right? Or there are probably other approaches that won't need that. And I welcome any input from this community on that point. Some of the other details we've applied for and have got access to the Anvil supercomputer in Purdue via this lovely access program that's NSF supported. And so we're going to use that system to do these simulations and apply adjoint tomography approaches. As Zoe said, especially in the last few years, we've had a great amplification in the amount of data. And so now we're running into big data problems, just dealing with all these cross correlations and stacking them, and all the data and the subproducts from the data. It's becoming a big data problem. So us trying to move it around and make it workable is something that's happening in real time, just given the scale and the frequency that we are working on. And so sorry to leave you all hanging, but just to let you know that the model is forthcoming, and we're quite excited in what we were able to show, in addition to all the other excellent work that's happened in the area within Oregon, and then move beyond that at some point. And that's it.
Awesome. Thank you, Pieter.
So with this presentation, I would like to go over a recent non-ergodic motion model that we recently developed that learns both from empirical observations and results from physics-based simulations. And tying it to the theme of this workshop, the main challenges that we identified through this work was first the need to develop a non-ergodic ground motion model with a high level of expressiveness in order to be able to capture complex physical effects that we see both in the observations and the simulations, but also incorporate constraints based on physics so that it can scale properly for scenarios that are not represented well in the training dataset. It's being able to scale to large datasets because with the simulations that we saw today, we can have hundreds of thousands to millions of recordings that the ground motion model we need to assimilate in order to learn the repeatable effects, and also being able to recognize that it learns through using homogeneous streams of data and that there are differences between empirical and simulated results. And that's particularly important because otherwise the simulations may overwhelm the final answer due to their sheer size. For this study, we focused on the Groningen gas field, which is a gas field in Netherlands. And what makes this area interesting is the high impedance contrast at around 1 kilometer deep that causes ground motion to amplify and trapped near the surface, and the salt layer at 3 kilometers depth, which is where the induced earthquakes are triggered. And we chose Groningen because we have access to a detailed 3D velocity model that we can use to run simulations. And we have a lot of information about building and occupancy, which we can then use to run a comprehensive risk analysis as a next phase of this project. But what I would like to also emphasize is that the framework that is presented here is not tied to Groningen. It's transferable to other regions with varying level of empirical and simulated data. As with all previous non-ergodic models, the description of the repeatable effects comes on the basis of a backbone model. And here we use the model by Bomer et al. 2022, which was trained on a small empirical dataset from earthquakes ranging from magnitude 2 to 3.5, and ground motions recorded between 0 and 20 kilometers. And we can see from the empirical data that there is a complex attenuation trend that they show, and even in the developers of the ergodic model try to capture it with some level of success. And through the non-ergodic model, the goal is to being able to capture these path effects even better. The 3D velocity model is representative of the region, and we can see here that it clearly shows a very sharp decrease in the shear wave velocity at the top 800 meters. So we introduced this velocity model to SpecFEM 3D, and first we ran a series of validation simulations to make sure that we tweak some of the input parameters, such as the corner frequency for induced earthquakes that was smaller than for natural earthquakes, to make sure that the ground motions that we get are reasonable. And we can see from the comparison of the ground motion and the frequency content of the produced ground motions, they are in a relative good agreement with simulated results. With the validation simulation completed, then we ran the production runs, which involved 98 simulations with hypocenters spaced across the area of interest, and they were resolved up to a maximum frequency of 7 Hertz. And that produced a synthetic ground motion catalog of 800,000 ground motions. And this illustrates one of the challenges that I pointed in the beginning of the presentation. Trying to learn and develop a non-ergodic ground motion model with all these synthetic ground motions directly would have required a covariance matrix that would have been 4.7 terabytes. And that's something that is not available in a personal computer, and it's even difficult to find in a high-performance computing environment, which illustrates the need to have efficient approximations. To address the first challenge, we focus on better characterizing the non-ergodic path effects. And we did that by developing a new kernel that explicitly captures the correlation between vectors that represent these paths. And in this development, we wanted to make sure that it captures both the dependence of the path effects in the source, in the location of the source and the site, the azimuthal dependence, but also it has a number of physical constraints, such as it enforces reciprocity. And the way that we formulated this kernel is that we assumed that there is an Gaussian field covering the 3D space in our domain of interest that represents these repeatable path effects, and the correlation between the path vectors is simply the integral along the paths that we are interested to compute. And in this figure, we can see the correlation structure that this kernel is providing, where we can see it's dependent both on the orientation of the two vectors, as well as the relative size between the size of the path and the length scale of this underlying field describing the path effects. Then the second challenge that we addressed was how can we scale Gaussian process regression to very large data set. So in Gaussian process regression, the equation that we need to solve is the one shown here, where y sub t is the training data set. And one way that we can understand this equation is that the prediction that we make is simply a linear combination of the observed ground motions. So if we can understand the structure of the weights for the observations, then we can find which of the observations are important and simply discard the negligible ones. And through our investigation, we found that these weights, alpha I, decay after, if we want to make a prediction at some location in the center, the weights decay rapidly after we go through the first set of observations. And so that means that the remaining can be treated as zero. And that makes physical sense. Essentially, what it says is that when we try to predict ground motion, we only care about the ground motions around that region of interest and not what is happening further away that we can simply discard. And so to achieve that, we developed an approximation scheme composed of two steps. First step is a screening where we find the recording with the highest degree of correlation, not considering that some of them may have mutual information. And then in step two, we further prune these selected ground motions, taking into account the mutual information that this ground motion may share. And through this, we developed an algorithm that scales in complexity linearly, both in terms of calculations and in memory. So the previous covariance matrix that was terabyte in size now can be simply represented as 10 megabytes without losing much accuracy. The last challenge to address is how do we train a non-ergodic model that is built based on both simulations and empirical data set. To do that, we decompose all of the systematic effects, so the source, the site, and the path, into three sub-pieces. And for each of them, we have a term that represents the real effects that simulations can capture. Then an additional term, which are the real effects that are not included in simulations due to simulation simplification, either in the velocity model or in the simulation itself, and then any artifacts that may be present in the simulation. And running the regression, we were able to successfully predict the ground motions for scenarios that we didn't include in the training. Here I'm showing the comparison between the residuals of the ground motion model for one of the scenarios and the mean prediction from our non-ergodic model, where within our domain of interest, we were able to capture the complex patterns that we see through the simulations. And we also were able to recover the residuals as a function of distance. Comparing it against the empirical data set, using the empirical data set alone led to a reduction in the aleatory variability of the model of about 40%, and including the simulation led to a further reduction, another 5% further reduction. And we also found that the simulations were most informative in constraining the path effects. And that was to be expected. There was zero correlation between the non-ergodic effects in the empirical and the simulated results in the source, because all the source effects in the simulations were modeled as point sources. And in the site, we also observed a reduced correlation, and that was because the simulations were tapered to a 500 meters per second shear wave velocity. And in conclusion, through this presentation, we developed a scheme for being able to develop non-ergodic models that can capture complex effects, and in particular in the path, and how they can be scaled efficiently to be able to ingest large amounts of data, and being able to learn non-ergodic effects through heterogeneous data streams. Thank you, and I'm happy to take any questions.
Awesome. Thank you so much. That was really great. We probably have time for a couple of questions, if anybody has some. I have one if nobody else has any. I'm wondering if you could speak to your thoughts on scaling this. So if if one were to use this in Cascadia, I'm assuming that the geographic scale would present additional challenges.
Um, we haven't tried it in Cascadia, but I believe the methodologies that we have developed should be able to scale in terms of data uh, and identify only the scenarios that really contribute to the prediction that you want to make. So I would expect that the tool should work well.
Awesome. Thank you. All right, so then we have our last talk, which will be given by Alice Gabriel, who will be speaking about near-instantaneous physics-based reduced order modeling for shake map, seismograms, dynamic rupture, and the seismic cycle.
Okay, perfect. Thank you. This is a short talk, so I won't be able to cover everything that I promised in my long title. I will focus on those parts that are most relevant to ground motion modeling, and this is work done in collaboration with Dave May's faculty at UCSD, John Rikoski, Johan Magen, Gabriel Hobson, who are students and postdocs here. I'd like to start just with a bit of motivation. Earthquake simulations, dynamic rupture simulations specifically, are exemplified on this slide, but in general, I'm becoming ever more computationally intensive. Here's just a couple of numbers that is showing this evolution based on simulations that I was involved in. We see 5 Hertz dynamic rupture simulations of the Turkey earthquakes requiring about 9 hours on a full Frontera if you really want to push it to 5 Hertz. And they're solved for 10 to the power of 12 degrees of freedom, so unknowns that we have to solve for. So these are large scale simulations that we are now performing routinely and also rapidly after large events. These simulations produce large synthetic data. Here's 2 examples, a complicated visualization of Ridgecrest dynamic rupture simulations and an analysis of really densely sampled synthetic seismograms. This is again Ridgecrest, the Ridgecrest main shock, and we can see if you're looking at corner frequency with this high resolution in space, we actually start to identify really interesting source effects that are visible far away from the actual fault system. And, these kind of models can produce easily tens of terabytes. Reducing that amount of data is possible using computer science techniques. We are interested in a couple of those, but we can't reduce it by a lot. You can see, there's a couple of ideas here, but we will always produce still terabytes of data. And this is challenging, of course, fair data sharing standards, but it's also an opportunity. And this is where the topic of this short presentation today is that we've been starting to use the output of these large-scale simulations using scientific machine learning techniques to be able to evaluate scenarios that we didn't model very fast, near real time. And of course, so we are in this space here, hybrid models combining machine learning and physics. So none of the existing nice physics-based simulations are actually efficient enough for real-time or early warning applications. And, we're also challenged in routine PSHA assessment. So CyberShake, for example, is pushing towards 2 Hertz, but these are week-long, month-long efforts if you want to set up a new physics-based PSHA campaign. However, as I just said, we can use the results of a few of these intensive computations to construct what we call surrogates. So these are, for example, reduced order models using the low dimensional information, which enables evaluation of scenarios that we didn't simulate past. This approach is pioneered for these kind of applications by Dave May. There's a short overview of what this will include. So we have to define our mathematical model, which variables we're interested in training the models for. We run a few what we call full order models. So these are high resolution simulations, and then we set up with reduced order models. This is not new, has origins in fluid mechanics, like many of the good things we're using in seismology. The goal is much faster evaluation while retaining the essential physics. If you're interested, I'm really happy to talk about the math behind that. Just as a quick note, the choice of basis, how to represent these families of solutions to partial differential equations and ground motion simulation. This is the wave equation. And this is just the classical applications. So the advantage of this specific scientific machine learning approach is that this is not a black box approach. This is verifiable scientific machine learning. We can use the same error analysis that has been established for interpolation theory. We implemented these methods in a scalable software that's open source using C and PETSI, which is a library, which is well established. We can now work with more than 1 billion degrees of freedom snapshots, and we have also a more accessible Python implementation. There are limitations to this specific method, extrapolation, so trying to learn completely unseen parameters that live outside of the parameter space are challenging. And you have to think a little bit about how you design your parameter space. So we currently can set up these reduced order models for parameter spaces of less than 10 dimensions. The first application are shake maps, published and led by John Witkowski. I have to really summarize this very quickly, but basically we've been training these models using 1 Hertz resolution 3D wave propagation simulations that account for topography, viscoelastic attenuation, 3D velocity model, up to down to 500 meters per second in shear wave speed, and varying earthquake point source locations and depths. And we can start to learn this peak ground velocity, for example, PGB maps. If you're comparing these scales here, you can see how much faster the ROM, the reduced order model, is. This is just an overview of how these workflows look like. Data collection in this case means collecting simulation output, constructing the basis, interpolating to unseen parameters, predicting. Here's an example of these different of our model setup. So this is just a relatively small domain, 30 kilometers times 30 kilometers in Southern California. And we've been looking at different complexities in the velocity model and how this method performs. What's really interesting is if you're comparing different machine learning approaches to interpolation, for example, random forest, multilayer perception, k-nearest neighbors with radial basis functions, we can see that this classic approach is superior in accuracy, independent of how complicated our forward simulations are. This allows us not only to get to shake maps really fast, we can also solve maximization problems. So this is, using ensemble forecasting. So for example, we might be interested in finding out what the worst case scenario in terms of shaking is if we are varying the depth of the same earthquake, and we're interested in the maximum shaking experience at the Clearwater power plant, which is just at the edge of our domain here. So we're interested in the tail of our distribution. And to look at these kind of things, we can evaluate millions of models and really quantify what, in this case, the worst case is. And we can also do global sensitivity analysis or forward uncertainty quantification. We have a USGS early warning proposal recommended for funding that will extend this approach to look if we can improve shake alert contours. So, just try to get to something a little bit more realistic, especially in regions with sedimentary basins than what is currently implemented. We've been extending this to time-dependent seismic wave propagation. It was published last year. We do this by splitting up our moment textures into 6 fundamental components, and then, doing the same reduced order modeling approach also in the time domain. And we can do this relatively efficiently. We compute Green's functions in this approach. And here's an example where for the application that we show in this paper, where we are constructing this ROM for this whole region. And now we allow sources everywhere in this part of the domain. And this allows us this rapid computation of seismograms that are accurate and that represent all of these possible sources really fast. And we account for geotechnical layers in this model setup too. So here's just an image of how this looks like. We have our exact forward model, our reduced order model. This is the error. And if you're looking at the seismograms and zooming in a bit, this is doing quite well. So the errors remain small in space, time, and frequency domain. This approach also allows us to simulate seismograms with kinematic finite fault models just by using the representation theorem to stack up our point source representations. You can do complicated source time functions like this one, where we have 2 pulses happening. That is actually the source time function of the moment magnitude 5.9 Whittier-Narrows earthquake. And you can see this comparison of the wave propagation of our expensive forward simulation and our reduced order model that was done in milliseconds here. And hopefully you don't see many differences. Now, this is our newest work. As I said, we've been setting these these reducer models up to learn Queen's functions. So the idea is that we can try and see if we can speed up CyberShake, which is a well-established PSHA tool. And a paper that is exploring that possibility is also led by John, has been just submitted to BSSA. So CyberShake hazard maps typically interpolate ground motion from relatively sparse grids, 335 sites. You can see this in this figure here. This typically looks like. So we've been building forward simulations and a reduced order model for 480,000 sites. So that allows us to look at ground motions at a 500-meter grid resolution in all of this blue box along the southern San Andreas Fault. And we can do this for large earthquakes because we can use this to represent kinematic sources. This is just one result that I have time to show. What we find is when we're comparing to, in this case, BA18 GMMM, that we see quite large non-ergodic effects. So for example, due to radiation patterns, the GMMs generally underpredict simulated spectra in deep basins like the Fillmore Basin. So that means that the interpolation that is used in CyberShake can miss some localized amplification near basin edges. In our analysis, that is up to a factor of 3 in terms of shaking. And these errors increase with frequency. So we've explored up to 1 Hertz in this study. This is explainable because wavelengths shorten relative to the station spacing if you go to higher frequencies. And using this reducer model approach enables this much higher resolution mapping, 336 times faster compared to just running more CyberShake simulations that would be using the standard reciprocity approach. We have an NSF project funded that will try to combine the simulated ground motions with observed ground motions. So we're using GAPI-POT. So these are methods that are stemming from engineering, and we have collaborators in engineering that will try to we will try to explore how we can combine simulated and observed data to inform these models. So in summary, these reduced order models are easy to use. They can be very accurate without needing vast volumes of training data, easy to interpret. They're verifiable, no black box. We have error estimates for them. They're fast, and we applied them so far to shake maps, seismic wave propagation, and then I didn't have time to talk about the dynamic rupture reduced order models and the slow slip cycle and seismic cycle simulation reduced order models, but we've also done those, and we have similar speed ups for dynamic rupture, even a factor of 10 to the 8 faster evaluation of these models. So we still need high quality, high performance computing simulations, but we can utilize few of these simulations much more efficiently by exploiting such approaches. Thank you for listening.
Wonderful. Thank you, Elise. Do we have any questions?
I can stop sharing. We had a 10-minute timeline, so sorry. I know it was a bit fast. But the slides will be uploaded.
Great, thank you. Looks like we have one question in the chat. How long would reduced order models take to run on 60 to 70 core CPUs?
Right. So once reduced order models are set up, you can evaluate them on your laptop. You don't need a HPC system anymore. You do need HPC systems to set them up in the first place, to run the forward models and then to train, to construct the reduced order models. But and I think this has a lot of potential also for other regions, that don't have access to high performance computing, because we could provide these kind of surrogates, and it would allow working with them without having access to large scale computing.
Oh, thank you. Great. Okay, so I think what we'll do is we'll transition to the breakouts. So to sort of give everybody context for this, the goal of these breakouts is, I can't find there we go, is sort of to combine questions for both portions of today's session. So one of them is on the inputs and the other is sort of next steps as a community. So what we're hoping to do is bring together folks that are working on developing ground motion models and some of the more seismology focused talks you saw today to talk about what are some of the things that we can do to address some of the needs that we identified last time in Breakout 1, and then what directions our research needs to take towards these in terms of what's feasible in the short term and then also the long term. So essentially, how do we take this seismology research and sort of turn it into the applied needs for ground motion modeling? And then the other set of questions are, what are our next steps as a community? So what are some of the key takeaways? And then also, what forms of interaction do we think are important to make this science applicable? So what we're going to do is split everybody up into 4 breakout rooms. We'll have some note takers, and I think we'll spend, let's see, probably 15 minutes or so in the breakouts, and then we'll come together and summarize at the end. So if note takers, if you could be ready to write a summary.
Well, sorry, Valerie, can I put you
Yeah,
on the spot for 1 second?
sure. Yeah.
Your first question on kind of what can we do to address the last workshop, do you mind just like summarizing one or two of those bullets you want us to hit on for people who might not have been here or can't remember?
Yeah, so actually let me put this up. So last time some of the things that we talked about were we split into these 3 breakout groups. So we were talking about what are the specific ground motion needs for the field, what characteristics are important, what do you see as the challenges, and it was within these 3 themes. So it was built environment, ground failure, and hazard and ground motion model needs. So if I'm remembering correctly, a lot of the things we talked about were site characterization. Some of them were sort of the frequency ranges and duration that we might need for ground failure and built environment. I don't know if anybody else who was in there has thoughts on some of the main takeaways from that.
There was also displacement requirements for tsunami,
Tsunamis, right?
and topography effects for ground motion prediction and landslide hazard.
Yeah. Anyone else? Or I'm trying to remember who else was leading some of the breakouts. I don't know if Karen or Norm or Aaron, if you have any recollections of things that I forgot.
Not off the top of my head. That
Okay.
sounds about right.
No, that was okay. That's fine.
Okay. Great. Yeah, so I think we'll head into the breakouts and we'll come back right around 10:55. All right, welcome back. We've got about 5 minutes to do a wrap up, and we've got 4 rooms. So I don't know if the leaders of each room would be willing to give a couple of main points from it. I think we could start with how they're numbered. So I think maybe, I don't know, Aaron, do you want to give them or I could give them?
I can try.
Okay.
Yeah, I think we had a really interesting conversation in our small little group. One thing that came up was we actually were talking in a little bit about Eastern Washington and Oregon, and how there's, including those areas, but also other areas, there's places where we need to refine shallow crustal structure. We also talked about, we had somebody from the Bureau of Rec, Wes, in our group, and how a lot of the infrastructure is in Eastern Washington and Oregon, and how they'll be impacted by long duration ground shaking from the Cascadia subduction zone. So in general, we were talking about some of the places that maybe are less talked about outside the Puget Lowland, in the CVN and simulations that need more attention. A few other things that we talked about was in terms of things that we could maybe do in 2 to 5 years. We talked about modifying GMMs using simulation data, what sort of maybe formalizing a framework for how you would do that, and kind of thinking through where do CVMs need to be improved in order to do that, what simulations would need to be run. We also talked about potential ways for improving that shallow crustal structure, our knowledge of that shallow crustal structure. I think somebody mentioned, I thought of it as a US array for basins or Willamette Valley or anywhere that you would like to better constrain, kind of marching around with short-term nodal deployments. Yeah, would anyone else in our group or Valerie like to chime in on other things that we talked about? But it was a fun but brief discussion.
I think that's pretty good. I think one of the other main takeaways for me is also speaking with the people that are sort of implementing it in a site-specific way and figuring out what is feasible and what does that sort of look like to be implementable in the future. Let's see, what is our next breakout? Maybe Norm and Emra, I think you were in a room together.
Yeah, I was taking notes. I can go over them. Basically, one of the things we discussed was extrapolation to large magnitudes and how we use like other region data and for this and with simulations. But most of our discussion was focused on what we can best use or how we can best use of the available data. And for this, like we were like only focused on so far like magnitude 4 or large events. Because of the absence of data, we may push to the lower magnitudes. And there was a question about, how well these smaller magnitudes would capture the high frequency content for calibrations, validations, or prediction purposes. That's something that needs to be explored. And for like best use of data also, differences, understanding the differences and transferable factors between California and Pacific Northwest, either through empirical data or physics-based simulations, can be helpful to guide the predictions in Pacific Northwest. And for this, Norm had a comment about maybe working in Fourier domain because it's a linear operation will be more preferable to better isolate some effects like magnitude scaling rather than response spectrum because there's more complications in there, especially with the duration coupling with the amplitudes. So
Awesome.
am I missing anything else, Norm?
Sounds like no.
Right.
I think we've only got 1 minute left. I don't know if the other groups, who'd be willing to go next.
I can just quickly add, I'll just add one comment. I wrote everything down, so this is recorded. But one comment that came up was quantifying uncertainties in the simulations. And there was the point made that a lot of the comparisons with simulations are done with GMMs. In some sense, there's some, it's a necessary comparison, but it also may not capture that the empirical data sets are pretty poorly constrained for large magnitudes. And so really making sure that the simulations reflect true uncertainties in our understanding for the region.
Thank you.
I
And I think it's
try and give the 30-second version of the fourth group, which is just to highlight a couple of things. One is we talked a bit about just improving our links across modeling approaches. Like how do we better honor kind of kinematic and dynamic rupture lessons for each other, or how do you include the geology, as well as just kind of coupled source modeling. Like can we get earthquake, tsunami sources that are coming from the same place? And so we're modeling kind of true hazard. The other is doing a bit better job with inputs. So one thing is Casey has revealed a different slab interface in Cascadia. And so how can we start modeling that and interrogating how and where those differences matter? Yeah, those are
awesome. That was great. Thank you so much. Yeah, so thanks again for coming. I think we'll have some more reminder emails to register for the in-person workshop in May, and hope to see you all there. Thank you so much for your time.
Okay.
Thank you.
Thanks.